chapter provides an introduction to probabilistic modeling, some basic concepts, and also a discussion of the axiomatic properties of trends satisfied by every triangle. We then also simulate a data set, a triangle, where we know what trends we simulate from. We also know the amount of random variability in the data, and then we go about modeling the data just to illustrate a number of statistical principles. So let me go to my PowerPoint display and start off with some basic principles. Now, let's suppose you only had one accident year's worth of data, and you had 13 observations at development year 0 to 13. In fact, these are the logarithms of the incremental paid losses. They could be the logarithms of the incremental counts, the logarithms of the incremental case reserve estimates, and so on. Okay, the basic thing is that they are logarithms. So at development year 0, we have this value. At development year 1, it's slightly lower, and so on. So we graph these 13 values in our spreadsheet, and they display the following pattern. And let's just try and see what the pattern is. And most of you, if you look at these 13 observations, will discern the following: that in the early years, up to about development year 4, on the average, the numbers seem to increase, and from development year 4 onwards, they seem, on the average, to be decreasing. So it seems that the kind of things you might want to do in your spreadsheet is actually estimate those true trend lines. So in your spreadsheet, we're going to estimate a trend line from development years 0 to 4, and the new trend starting at development year 4 all the way to development year 12. Now, for the sake of argument, so I can remember these estimates, let's suppose that the slope of this trend line, the one that goes upwards, is 0.3. The standard deviation of the trend estimate given by Excel, your spreadsheet, is 0.03. So let's call this 30% plus minus 3%, and let's suppose this is minus 20 plus minus 2%. So the first thing that Excel has done for us is actually estimated the two trend lines that intersect at development 4. Another calculation that Excel will do automatically is, if you're doing a regression in Excel, is calculate the observed minus the fitted, each one of these deviations, observed minus fitted, square them, add them all up, and divide by the number of observations minus the number of parameters, which are 3 in this case. Each line has an intercept and a slope. Because the two lines are constrained to intersect at development year 4, there's actually only 3 parameters. This is called the variance of the observations around the two trend lines. Now, if the variance is 0, all it means is that all the points sit on the trend lines. Now, if the variance is large, some large number, it does not mean that the fit is not good, because the variance becomes part of the model. The volatility around the trend lines represented by the variance is part of the model. It might be relatively large on the log scale, it might be relatively small, but that is part of the model. So in Excel, we've actually calculated two features in the data. The first feature is the trend structure. The other feature is the variability, the volatility, represented by the variance around those two trend lines. In Excel, we might also test these residuals, differences between observed and fitted. For normality, let's suppose they pass the test. There's no statistical evidence to reject the null hypothesis, and we can then postulate the following model. We would argue that at development year 0, the observation that we have doesn't sit on the trend line, but it's a random number from a normal distribution. The mean is on the trend line, and the variance we calculated in Excel on the previous sheet. At development year 1, we also have a normal distribution, but this normal distribution has a mean 30% larger than this one, because the trend is 0.3. This distance is 1. When we go to the next cell, we also have a normal distribution with a different mean. Again, the mean being on the trend line, again 30% higher than this one, but the variance being the same, and so on. So even though we only have one observation per cell, we actually have fitted, our model has fitted a distribution to every cell. And we're actually going to argue that these observations come from their respective fitted normal distributions. That's the model. How are these normal distributions related? Well, for instance, to go from this development year to this one, how do we go from this normal to this normal? Well, we have to climb up the trend line 30% so many years, and then go down 30% for so many years. All right, what we're going to do now, I mean, given that we are arguing that these observations come from their respective normal distributions, we're now going to simulate a whole accident year using these normal distributions. So you go into development year 0, and you simulate a value from that distribution, and let's suppose it sits below the mean, and it's the circle. When you go to the next development year, because it has a mean 30% larger, or 0.3 larger, it's likely but not necessary, it's very likely but not necessary, that this observation will be higher than this circle. Well, let's put it here, and so on. So we're going to simulate 13 circles, and so on, from each distribution. Now, if we were to graph just the 13 circles and just look at the circles versus development year, what we will notice, I guess what we will notice in the circles, just in the circles, is that if we fit the upward trend in the circles, the estimate of the trend will also be about 30%. Let's suppose 28% plus minus 2. If we fit the downward trend in the circles, instead of being minus 20, let's suppose it's minus 19 plus minus 2.5. There's another feature in the circles which corresponds to a feature in the x's, and that is if you measure the variance of their circles around their trend lines, it'll be statistically the same as the variance of the x's around their trend lines. So what I'm going to actually argue is you can't distinguish between the features in the circles, which is the simulated data, and the features in the x's, which is the real data, because you're actually arguing that these values actually come from the same distributions, the same respective distributions, a different distribution for each period. So if we conduct the following experiment, we go to somebody else that doesn't know about this problem, and we tell them that we do not tell them whether the x's are the real data or the circles are the real data. So we don't tell them which is the real, which was simulated. But this is the information we do provide for them. We tell them that if the x's are the real data, what we've done is we've estimated 2 trend lines for the x's, measured the variance around the trend lines, tested for the normality of the residuals, and simulated the circles from those respective normal distributions. However, if the circles are really the company's data, we fitted the 2 trend lines for the circles, intersecting at development year 4. We measured the variance, we tested for normality, and then simulated the x's from those normal distributions. Would that person be able to tell us which is which? And the answer is in the negative, no, because the model, if you like, is the good model. The data, the real data, the x's and the circles have the same features. Which features? Trend structure and the variability around the trends. Of course, if the model wasn't a good model, you would be able to tell the difference. Okay, and this is very important. We always do that in statistics, actually. Let's look at another simple example where you look at a line of business you pay for, immediately the accident happens. So these are just your severities, n severities, x sub 1 to x sub n. You fit a number of distributions to these severities. You test for quality of fits, and just for the sake of argument, it turns out that the log normal gives you a good fit. Did the log normal create the severities? The answer is no. Whatever created the severities, the underlying generating process is very complicated. So what do we mean that the log normal gives us a good fit? What we're actually saying is we can regard the x's as a random sample from the fitted distributions. Conversely, we're saying that the fitted distribution has probabilistic mechanisms for creating this real data as a sample. If, for instance, the largest value in your sample was 100K, 100,000, you would use the fitted distribution to calculate reinsurance premiums. Okay, suppose we now simulate n values from the fitted distribution. And again, we go to another person. We don't tell him which is the real and which is the simulated. We say to him, look, if this is the real data, the x's are the real data, we fitted a log normal to the x's, gave us a great fit. We then simulated the y's from the fitted. However, if the y's actually are the real data, we fitted a log normal to the y's and then generated the x's from that fitted distribution. Which is which? Well, they can't tell us, and if they could, it wouldn't be a very good model. It's the same here. Excuse me. We're going to design a probabilistic model for real data. What would be the features in the model? The trend structure in the 3 directions. A triangle has 3 directions: development year, accident year, and calendar years. We're also going to measure, the model will also include the volatility around the trend lines, the variance, in terms of normal distributions with possibly this time changing variances. We're then going to simulate 2 triangles from the model. If I take these 3 triangles to another person who has this product, Icopus Plus, they will not be able to distinguish between the 3 triangles. Why? Because they have the same features. Which features? Trend structure and also volatility around the trends. Let's look at an example. Suppose the real data has a trend change of 10% to 15%, say, in the calendar year 1994. So this is the calendar year 1994. 1994. Well, the simulated data will also have a trend change in 1994. Maybe not exactly from 10 to 15, but it could be 10.5 to 14.8. So simulated data will also have a trend change around 1994, I should say, also around 10 to 15%. The other thing that will be the same in each triangle, if I complete the square in each triangle, what else is going to be the same? The distributions of the total outstanding reserves for each triangle statistically should be the same. You shouldn't be able to distinguish between them because they all have the same features. Suppose another actuary comes along and he designs a model on the real data, but he uses some kind of ratio scheme. Then using some kind of ratio, link ratio scheme, he simulates his triangle. You can make the ratios fixed and add a random components of the ratios, or you can draw ratios from some mean and some standard deviation. I don't care what the distribution is. I don't really care who even does it. He will create his simulated triangle using his ratios that he estimated for the real data. We now take these 4 triangles, real, S1, S2, and S3, to another actuary that has this product and is familiar with this product. What will he be able, or she be able to tell us? In about 10 seconds for each triangle, this is what they'll be able to tell us. I can't tell you the difference between these 3 triangles. They have the same features, but I can tell you that this is the odd man out. What does that mean? It basically means that this one has features not carried by these 3 triangles, and there are features in these 3 triangles not carried by this one. There's no one-to-one correspondence. So this one has nothing to do, S3 has nothing to do with S1, S2, or the real data. In fact, if you took S3, and used it in ELRF, where is ELRF? The ELRF module of Icopus. If you use the ELRF module, you'll be able to estimate the ratios that the actuary used, or get estimates of the ratios that the actuary used to simulate the data, and you'll also be able to tell him almost instantly that this is not real data. Okay, let's go back to our original display. Okay, let's go to this display. Now, this is an introduction to the probabilistic trend family, so the first thing we're going to study here is the trend behavior, or the axiomatic trend properties of any triangle. Now, this is taken out of a modern statistical textbook. Actually, it's not so modern anymore because it was written in 1989. Now, forecasting the future can be likened to driving a car. The windscreen is opaque. Actuary sits in the back seat, looks out the back window, and he tells you where to go. If you see a straight road for many miles, you'll probably tell the driver to continue to driving straight, but you're not absolutely sure. If you see a road changing direction haphazardly, you don't know where you are, most people would say, oh, well, I'll tell the driver to stop. Well, that's only if you want to be liquidated. You can't actually stop because you've already written those years. What do I mean by straight road? I mean a stable trend. So if you look out your window and you see a straight trend for 10 years, what does that mean? 5 years ago, you should be able to predict the distributions of the observations in the last 5 years, and not only that, beyond the year, say 2004, you should get the same reserve distribution as if you were sitting in your motor car in 2004. Okay, vis-a-vis, say, sitting in your motor car in 1995. Now, if your trend is unstable, then you need to try and find out what caused the changes in trends. It could be by studying, for instance, closed claim counts. Sometimes they might give you an idea. Although it's very rare that closed claim counts change trends in paid losses. But, you know, very occasionally it does happen. So when you've got unstable trends and you, in fact, do not know what caused those changes and you don't understand the nature of the changes, it's very hard to call the future. And this is probably when you want to get reinsurance and make sure that the reinsurer does not have this product so they can't find out what's in your business. Now, whether your trends are stable or not, and I state this emphatically, whether your trends are stable or not has nothing to do with the volatility of the numbers, paid losses, say, and the volatility of the ratios. Bear in mind that with Equifax, after measuring the past volatility, you use the past volatility or variability to forecast the future volatility. We use the volatility in the past to forecast the future volatility. Volatility is synonymous with variability. So again, stability of trends has nothing to do with the stability of numbers or stability of the ratio. So we are going to show you, perhaps in chapter 4 or 5, a very volatile set of numbers, yet the trend is pretty stable, so that 9 calendar periods ago we would have got the same reserve distributions beyond the current year, and we would have projected the distributions of the 161 observations we left out. A triangle has 3 directions: development year, accident year, and calendar years. Now, if the evaluation period is 1998, you're sitting in your motor car here in 1998. All paid losses made in that year are made in the same year. All closed claim counts, same year. Case reserve estimates estimated in the same year. Next year, you'll drive the additional mile. Of course, if you don't want to write any more business, you still have to drive forward, and you'll be with your motor car here. The past is up the diagonals that way. This is the future. If there's a bout of economic inflation that manifests into the paid losses between 86 and 87, it's a trend. If there's a bout of social inflation, it's a trend. So how do trends work for a triangle? So the first triangle that we're going to look at, we actually simulate. You can see all the numbers in every accident year. If you look at a particular development year, the numbers going down the different accident years are the same. It's generated by this exponential curve, the exponential of alpha minus 0.2 by development year. I chose alpha to be 11.513, so that the exponential of 11.513 is 100,000. On a log scale, you can see the accident years are homogeneous. The way I can represent these numbers graphically is that there's a straight line with a decay of 20%, and the intercept is 11.513. How can I represent these numbers to a CFO or to a CEO and everybody else in the company? Remember, a model is a story about the data. It's a summary of the features in the data. How can I summarize these 90-odd numbers? Very easily. I could argue that along each development year on a log scale, there's a uniform decay of 20% for every accident year. And every accident year starts with the same number, 11.513 on a log scale and 100,000. So by just giving two numbers to somebody else, I've described the 90 odd numbers. And that's a pretty brief summary. Okay. And that's what a model's supposed to do. Suppose we add a trends along the calendar year, 10% for the first 4 years. Incidentally, this is all discussed in the paper Best Estimate for Reserves. 10% for the first 4 years, 30% between the next two, 15% for the next 8. Trends on a log scale are straight lines. What happens to the numbers now? So we're going to be studying the axiomatic properties of trends. And this is what happens to real numbers, and you'll see it in one of the chapters, in one of the demonstration chapters. Now, when we go from this development year to the next development year in the same accident year, 1978, we are in fact moving to the next calendar year. Therefore, that trend of 10% along the calendar years manifests itself also along the development years. That's an axiom. But it also manifests itself along the accident years. So the first axiom we're learning is that any calendar year trend projects in the other two directions. And that's true for any real data set. Any real data set. Given that it's true for any real data set, it also must be true for our models. Let's calculate some resultant trends now. You might remember that at school you learned about vectors or resultant vectors. Well, I guess this is akin to that. If I move along these development years in 1978, the resultant trend is minus 20 plus 10, which is minus 10. Between these two development years, minus 20 plus 30 is now plus 10, so it actually goes up. Along these development years, minus 20 plus 10 is minus 5, so just a little bit of algebra. The next accident year must be 10% higher, and now the 30% trend for the next accident year kicks in one development year earlier. Let's look at the graphs. This is all done in a spreadsheet. First accident year 78, minus 10, plus 10, minus 5. Next year's 0.1 higher. But can you see the plus 10 is always one development year earlier? Every accident year is now different. Now, if you look at 1983, what happened to 1983? Well, 1983 is already going to the 30% change. So the trend here now is just the minus 20 plus the 15, which is minus 5. Let's erase some of this. What's the resultant trend going this way? Well, from there to there, you are going to the next accident year, same development year, but also the next calendar year. So it's 15, 15. What's this trend? 30, 15, 15, 15. This is what in Chapter 2 we call condition 3. As you go down the development years, the trends change at different calendar years. What about here? 10, 10, 30, 15, 15, 15. You'll see that in the graph. Choose development year 7. As you step down the accident years, it's always 0.15. If instead you select development year 4, it's 0.3, 0.15, 0.15, 0.15. If you select development year 1, it's 0.1, 0.1, 0.1, 0.3, 0.15. This is very important. Anytime there's a change in calendar year trends, the accident years that go through those calendar years are different. The resultant trends are different. This blue year is very different to the yellow year. It's very different to this year. Okay, just as a matter of interest here, suppose we accumulated the numbers for every accident year along the development years. What would be the relationship between this cumulative and that cumulative? Extremely complicated, extremely complicated. Because you've got to exponentiate all the numbers and add them. The relationship is extremely complicated. Yet on a log scale, the incrementals are related. 10%, 30%, 15%. Do you remember that first study we did when we only had one accident here? We had 30, 30, 30, 30, minus 20, minus 20. Well, it's the same kind of relationship. What we're going to do now is add some random numbers to those trends that come from a normal distribution with mean 0 and variance 0.01. And now we look at the graphs. Now, what have we learned? We've learned that if we look at this blue accident here, what are we looking at? We're not just looking at the trends in the actual accident year itself, because whatever trends are in, so we're not really looking at the trends for the accident year along the development years, which is just a -20. On top of that, we also have the calendar year trends, and on top of that, randomness. So anytime you look at real data, if you graph the incrementals for an accident year versus development year, you're not just looking at what is happening in the accident year, because whatever is going on in those calendar years gets projected on top, and that's an axiom, which is more powerful than a theorem. What we're going to do now is actually model these numbers, and what are our expectations when we model those numbers? Those numbers will deviate randomly from the true trends. What do we expect? Suppose we model the numbers now that deviate randomly from the true trends. We know the true trends. What are our expectations? If we were to estimate this trend, we'd expect the estimate of this trend to be approximately -20, the estimate of this trend to be approximately 10, the estimate of this trend to be approximately 30, and the estimate of this trend to be approximately 15%. So if we were to estimate the base development year trend, the 3 calendar year trends, the estimate of the trend from 83 to 91 would expect to be approximately 15%, maybe 14.8 plus minus something. Supposing now we take our car backwards to 1987. And now we don't have this data. And only estimate the trend now along the development years, the 10, the 30, and the calendar year trend from 83 to 87, the estimate would still be statistically the same or close to the 15%. Statistically the same as the estimate from 83 to 91. When we then do our projection of the reserves beyond 1991 at the end of 87, statistically, we would expect the same distributions as if we were sitting with our motor car at the end of 1991, because we are still on the same trend line. Let me remove some of this clutter. So summarize, you're sitting with your motor car there, have an estimate of this trend and the other trends. It's approximately 15. You do your projection for that region beyond 1991. You expect about the same reserve distributions as if you were sitting with your motor car there. And not only that, you'd expect to do a pretty good prediction, and I'll define what I mean by an accurate or pretty good prediction later on of the observations you leave out. Let's make it more complicated. What if you're sitting with your motor car at the end of 83? Well, you don't know about the 15% trend. What do you know? You have an estimate of the -20, an estimate of the 10, an estimate of the 30. Suppose the estimate of the 10 was 8 plus minus 5, and the estimate of the 30 was 40 plus minus 10. What do you do now? Well, there's been a major trend shift. Suppose you found an explanation for it. New legislation. You've standard legislation. Usually new legislation is a one-year effect. And in that context, you probably would, by judgment, decide to revert to the old trend, which is the estimate being 8 plus minus 5. So at the end of 83, you'd assume that the future trend comes from a normal distribution with mean 8% and standard deviation 5%. You don't know it exactly. Suppose you did that. Okay. At the end of 84, when you move 1 year into the future, you might have some evidence that it's a bit stronger. But definitely you'll have that evidence by the time you get to 87. Let's do it. So here's the data. I'll go to my database. It's a demonstration database. It's called M3IR5. And I'll open it. And that data was actually simulated in Excel. There it is. Now we know that since 83, there's a 15% trend there on the log scale. Why is this number in development year 1, 1990, smaller than the previous number? The reason it's smaller is because when you have randomness around a trend, successive numbers are not necessarily larger. So you've got the 10%, 30%, and 15%. This number doesn't have to be larger than that number. In fact, if the normal distributions had a relatively large variance, you could imagine that a number here in this year could be much larger than the next number in a subsequent year, yet you do have an average of 15% trend. Now what we're going to do now is we're going to go to PTF, where by default we've already estimated a model. And you'll see a little bit more later, and you get a bit of understanding as we move forward. You can see that along the development years, there's a grey band here that tells us that the model we've estimated, it's called a default starting model, has a trend parameter between development years 0 and 1. Thereafter, there aren't any more grey bands, so the model we've estimated only has one trend along all the development years. So that would be an estimate of that minus 20. Along the accident years, we only have one accident year level parameter. Along the accident years, we have level parameters. Level parameters are parameters for years. Trend parameters are parameters between years. Along the calendar years, we only have one trend parameter. But we know that in our data, we have three trends, the 10, the 30, and the 15. So if we only estimate one, we are estimating the average. Now, you can calculate algebraically the average of 10% for 4 years, 30% for between 2 years, and 15% for 8 years. Well, the average would be 0.1 multiplied by 4 plus 0.3 plus 0.15 multiplied by 8 divided by 13. But by eye, you should be able to calculate the average approximately. Bear in mind that you had the 15% for 8 years, so it'll be heavily weighted towards the 15%. So you'd expect the average probably to be slightly larger than 15%. Okay, but not very close to the 30. You only had that between 2 years, and the 10% you only had for 4 years. All right, so let's see what it is. Well, we have a model display, and the model display tells us that this is a development year trend, which is pretty close to the minus 20 in the real data that we used to generate the data. I said real data. Well, you'll see later on that you couldn't distinguish this from real data. In other words, real data is generated by these kind of models. If you look at the calendar year trend, it's 15.63%. Now, what's a residual? A residual, I mean, a lot of people think of residuals as they have to be random if the model is good. But residuals are much more than that. This is the way residuals should always be interpreted. You know, regression is also used as a form of adjustment. It's very powerful as a way of adjusting data. So think of residuals as the data minus what I fitted to the data. Always think of residuals that way. What did I fit to the data? Well, to the data I fitted a 15.63% trend. There it is here, the straight line. What's a residual? A residual is going to be my data minus the 15.63% trend that I fitted to the data. Well, let's see. For these years that climb up at 10%, 10% minus 15.63% will be minus 5.63%. So the data here minus the fitted value, the fitted trend, should be around minus 5.63%. 30% minus 15.63% is just over 14%. For these years where you have the 15% trend, when you subtract 15.63, it's close to 0. It's slightly negative. So the residuals here would trend downwards negatively, positively, around 0. Let's see what happens. So let's look at the residuals. So these are the residuals, which the data trends up at around 10%. We subtract 15.63%, so that's our minus 5.63. Then from 82 to 83, there's a positive trend, probably close to that 30 minus 15.63, just about 14%. And you can see that 15 minus 15.63 overall is slightly negative. So that suggests to you there's a trend change here. So we add another parameter. But you don't believe the trend goes all the way from 82 to 83 all the way upwards, so you add another parameter here. We're just designing a new model. We're going to estimate it, and we check the model display, and now we've estimated 8.73 plus minus 2, 39 plus minus 4.42, and 14.46 with the lowest standard deviation. Why is the estimate of 30 so far away of 30? And the reason it is so far away, because we only had the 30% trend between the 2 years 82 and 83, and we only had very few data points. It was in the early years, so there was also high uncertainty associated with that estimate. Let's look at the model display. There are 4 graphs. The development year trend, accident year levels are constant, however there are changes in the calendar years. And remember that calendar year trends project along the accident years and development years. An integral part of the model is the volatility around the trends. That's the variance of the normal distributions. Do we have normal distributions? Well, I hope we do, because I did simulate from normal distributions, simulated values from a normal distribution with mean 0 and variance 0.01, and added those to the trends, and that's what we were modeling. Okay, this is the variance of the normal distribution. 0.0096. The standard deviation is just under 0.1, so the coefficient of variation of the log normal on the Dole scale is at least 10%. Okay, but a model, there are 4 pictures. Any 3 of the pictures on their own are meaningless. If you want to look at the model display in 3 dimensions, you'll see something you saw in the PowerPoint display. You notice now that the calendar year trends project in the other 2 directions, and this is the same as what we have here. Now, what about the data? Let's go back to the data, and I'll plot the data in 3 dimensions on a log scale. So what we in fact have done is we've extracted this trend structure the trend structures on the left. We've extracted that from the data. So the data looks a little bit like dog's breakfast due to the randomness, but that's the trend structure in the data. Now, let's bring up the regression table, which has become kind of superfluous. Let's remove the residuals for a moment. The gammas, you can see by this arrow, the development year parameters. There's only one in the table. There's only one in the graph. The alphas are the accident year parameters. Incidentally, I don't expect you to understand everything and appreciate everything right now. It does take time. As I show you more, you will learn more. But even by the end of the whole demonstration, which is about 3.5 to 4 hours, there's a lot of things here that take a lot of time to absorb. It does take time. So don't get particularly concerned if there's a lot of things, a lot of issues you don't particularly understand. You can always send us an email and we'll try and answer your questions. The iotas are the calendar year parameters. There's only one. Sorry, there are 3. You can see 3 in there. There are 3 in the graphs. Now, there's a logbook also, and in the logbook we just have some summary statistics. For instance, the logbook tells us that the trend between the last 2 development years is that. But if you look at the structure of your model, that's actually the trend not just between development years 12 and 13, it's along all development years. If you now go to the iota last, that's the trend between the last 2 calendar years. Well, actually, that's more than the trend just between the last 2 calendar years. It's the trend since 1983, because we only have one trend parameter starting in 1983, finishing in 1991. When we want to do the forecasting, we have a lot of options. Let's view these. The triangle is 0 to 13 development years, so it has 14 in total. One option is how far do you want to forecast that way. Another option is, for instance, if Equitas is assuming the risk of the 92 in prior years for the London syndicates, or its syndicates, well, the syndicate might have the whole triangle, but you're only interested in these reserve distributions. I mean, from the point of view of outstanding of reinsurance, you might only be interested in the reserve distributions by calendar year and accident year, just for the last 2 accident years, because that's where your bulk of the reserves are. For pricing, you can go forward. That's another option. And keep in mind that any calendar year trend projects in the other 2 directions, so it projects along the accident years. Another option is, do you want to continue with that trend? Remember, if you're at the end of the year 82, 83, where you had the 30% trend, you might want to revert to a prior trend. Another option, do you want to create the combined table? In other words, if you want to, say, create some kind of reinsurance program which is simultaneously retrospective and prospective, you want to look at the combined table of reserves plus future underwriting years. Okay, well, we'll just complete the forecasting table. In every cell there are two numbers. A black number is an observed. It's the mean of a log normal. How do we know that? Because on a log scale we have normal distributions. On a dollar scale we have log normals. That's an observed. On the right side of the table, the black is the mean of a log normal. The red is the standard deviation of the log normal distribution you are projecting for that cell. So we've used the model, this picture, 4 pictures I should say, to project distributions in every cell, and these distributions are correlated. These are calendar year sums, the mean and standard deviation, but these are sums of log normals that are correlated. To find out their distributions, we'll do that later for simulations from these log normals. These are reserves, blacks are means, burgundies or browns are standard deviations, ultimates, forecast summaries by accident year, calendar years, summary graphs, go to the logbook, and we find that the mean of the reserve distribution is 23.4 million, and the standard deviation of the reserve distribution is 927.8 thousand. What we're going to do now is leave out the last calendar year. We're going to take our car backwards 1 year. Now, instead of estimating a trend of around 14.46 from 83 to 91, if we're going to leave out this year, we're now going to only estimate the trend from 83 to 90 without that year 1991. Would we expect the estimate to go up or to go down? Well, let's just see now. If you look at the last year, you can see that the last year is relatively low. So if we leave out a lower year, we'd expect the estimate to go up. So let's estimate it, forecast. Okay, if you look at the logbook, you'll see that the estimate's going up from 14.46 to 15.27. That's one of the reasons we get a high mean reserve. The reason the standard deviation enlarges, gets larger, is because we've got more parameter uncertainty, and also the forecasting horizon is further away, because now you're really sitting at the end of 1990, you have given 0 weight to the observations in the last calendar year, so you're further away. Let's give 0 weight to the last 4 years. Estimate, forecast. Bear in mind that the blue values in the last 4 calendar years have been left out. They have not been used. Let's look at the logbook. We find that the mean reserve has gone up slightly more. We've left out, if you look at the N here, we've left out, we've gone from 105 to 55 observations here on the left. Let's go back to the right. The mean reserve has gone up slightly, the standard deviation much larger. But also our estimate of the trend has gone up from 14.46 to 15.63. That's why we're also getting a high answer. How well would we forecast the last 4 years 4 years ago? This is called validation analysis. What we've been doing, the removal of years, is called validation analysis. If you click on V, you look at the prediction errors. You're sitting with your motor car at the end of 87, and you're looking down at the diagonals, and you're looking at the prediction errors. Observed minus predicted, standardized. And you can see they're slightly skewed, they're slightly negatively skewed, so you're doing a little bit of over-prediction. Well, it kind of makes sense you're doing some over-prediction, because all of a sudden your estimate of the trend goes from 14.46 to 15.63. So you might argue, hold on a minute, if I left out the last 4 years, my estimate of the trend increases since the trend since 1983 increases if I leave out the last 4 years. The last 4 years are actually pushing the estimate down. Is it therefore possible that the trend has come down 4 years ago? It's lower in the last 4 years. Well, I know that I didn't change the trend. I used the 15% to simulate the data, but you might not know that, so you might want to go to test it. So let's test it. Let's test it. You add another parameter. You undo the 0 weight. You estimate. If you now look at the regression table, you look at the iotas, the estimate here is 15.82, and here it is substantially lower. But the pink line tells you there's no statistical evidence of a trend change. Well, that's good, because I didn't change the trend. So the estimate only changed due to the random variation or the volatility around the trend line. If you go to the model display, you'll see the same story. You have a pink line here telling you that this trend, or the difference in trend, last line in their caption, is not significant. So if you click on O, it optimizes the model and removes that parameter that you didn't need in the first instance. Okay, well, this is the end of this particular chapter. In the next chapter, we'll be modeling some real data and then also using a wizard. And then we'll also going to be looking at some subsequent study of some very volatile numbers where the trend, in fact, is very stable. Thank you.